Hello all these students. Today we are going to do some more problems on posets. So let's start. I'll start with the problem number 1. It says I have to find, I am given some relations on sets and I have to find out of these which one are posets. Okay, so these are the 4 relations on sets A, B, C, D. Out of all these 4 relations, I have to find out which of these are posets. The first one is the relation equals to, which is on set Z. So I have to find out whether Z comma equal to, which is the relation. Here equal to is the relation on set Z. So Z comma equal to is a poset or not. Then R comma less than is a poset or not. Then C, Z comma not equal to is a poset or not, and D comma Z and D, Z comma greater than or equal to is a poset or not. So we'll start with the first one. Now for Z comma equal to be poset, if this has to be a poset, then the relation here equal to is the relation and Z is the set of integers on which this relation is formed. Okay, so because we know that a relation is always formed on some set, so equal to is the relation here and Z is the set of integers on which the relation is formed. So if this relation, if I give it name R, if I give this relation name R, so if R is a partial order, then I can say that Z comma equal to is a poset. Fine. So let's start. So here that means the criteria for the formation of relation is the equality symbol. So that means R, that means I can say that R is a set of ordered pair AB. R is a set of ordered pair AB such that A is equal to B. Okay, so since we are running out of space, so I'll erase all of this and start with the first option. So the first problem says that I have to prove that Z comma equal to is a poset. Okay, so the first, then I know that the relation here is, relation set consists of ordered pairs AB such that A equals to B, because this is the criteria for the relation to be formed here, right? Okay, so I know that R will be a partial order if it meets 3 conditions. That means if it is reflexive, if it is anti-symmetric, and if it is transitive. So first of all, I'll see if it is reflexive or not. So to be reflexive, an ordered pair AA must exist in the relation, right? That means A is equal to A, and here I am saying that A equals to B. So that means I am meeting the criteria for this to be reflexive. So I can say that yes, it is reflexive. Then I will see if it is anti-symmetric or not. Now to be anti-symmetric, if an ordered pair AB exists in the relation, then the ordered pair BA must not exist in the relation, right? If the ordered pair AB exists in the relation, then the ordered pair BA must not exist in the relation. And if BA is existing in the relation, right, then in that case A must be equal to B. So here I know A is equals to B, hence I can say that yes, it is anti-symmetric also. Next, I will see if it is transitive or not. To be transitive, if the ordered pair AB and ordered pair BC exists in the relation, then the ordered pair AC must also exist in the relation. So I can say that if A equals to B and B equals to C, then obviously A is equals to C. So that means if ordered pair AB exists and ordered pair BC exists, then ordered pair AC will obviously exist. So it is transitive also. Since it is reflexive, antisymmetric and transitive, so I can say that this relation R is a partial order, right? And if this relation R is a partial order, then I can say that Z comma equal to is a poset. So hence this is a poset. Now let's look at the other problem. Let's look at the other problem which says R comma less than. Now here I have to prove if R comma less than is a poset. So again for that, now R here is the set of real numbers. When I say R here means the set of real numbers, and this less than is the relation which is formed on the set of real numbers. Now let us give this relation the name R1. Okay, let us give it the name R1. Now the basis or the criteria for the formation of this relation is the less than symbol. That means relation R1 consists of ordered pairs AB such that A is always less than B. Now in order to prove that R comma less than is a poset, I have to prove that R1 is a partial order. And in order to be a partial order, it should be reflexive, antisymmetric and transitive. So let's see if it is reflexive. Okay, so to be reflexive, ordered pair AA must exist. Okay, for all A that belongs to the set of real numbers, an ordered pair A comma A must exist in the relation. So that means A equals to A. If A comma A exists, that means A is equal to A. But here A is not equals to A, rather it is less than B. So that means it is not reflexive. Then we will see if it is antisymmetric or not. Now to be antisymmetric, if the ordered pair AB exists in the relation, then the ordered pair BA must not exist in the relation. And if BA exists, in that case A and B must be equal, or A must be equal to B. Now let us see. If I say A is less than B, then it's quite obvious that B cannot be less than A. That means if AB exists, then BA cannot exist in this relation. Hence, yes, it is antisymmetric. Okay, now let's see if it is transitive or not. Now if A is less than B and B is less than C, then it is quite obvious then A would also be less than C. So yes, this is transitive, but it is not reflexive. Now this relation R1 is antisymmetric and transitive, but it is not reflexive. Hence it is not a partial order, and therefore R comma less than is not a poset. Now let's see one more problem. Here I have to prove that Z comma not equal to is a poset. Now again I know that Z is the set of integers here, and this not equal to is the relation which is formed on the set of integers. And to prove that z comma not equal to is a poset, I have to prove that this relation is a partial order. Now let us give the name R to this relation. Now I know that the criteria for the formation of this relation is that A is not equal to B. So that means R is a set of ordered pairs such that A is not equal to B. Now let us see if it is reflexive. To be reflexive, ordered pair AA must exist, and that means that A is equal to A. But here A is not equal to B, right? So the ordered pair, elements of the ordered pair are not equal over here. That means it is not reflexive. Okay. Now let's see if it is anti-symmetric. Now I know again to be anti-symmetric, AB, if AB exists, then BA must not exist. And if BA exists, then A must be equal to B, right? So that means if A is not equal to B, that is quite obvious that B is also not equal to A. Yes? If A is not equals to B, it's quite obvious that BA is not equals to A. Hence, if I can say that if AB exists, then BA is also existing. So hence, it is not anti-symmetric. Okay, now let's see the third condition criteria, if it is transitive or not. Now, as per transitivity, I say that if A is not equals to B and B is not equals to C, then can I say that A is not equals to C? It seems like it is quite obvious that if A is not equal to B and B is not equals to C, then A is not equals to C. But it is not always true. Now let us take an example. If 1 is not equal to 2 and 2 is not equals to 1, then can I say that 1 is also not equals to 1? No, 1 is equals to 1. So it is not transitive also. Now since it is not reflexive, neither anti-symmetric nor transitive, so it is clearly not a partial order, and hence z comma not equals to is not a poset. Okay, now let's look at the last problem of this problem 1, which says z comma greater than equal to. Now I have to see whether z comma greater than equal to is a poset or not. So again, z is the set of integers and greater than equal to is the relation which is formed on this set of integers. Now again, if I give this relation name R, then I know that greater than equal to is the criteria for the formation of this relation. Hence I can say that R is a relation set which consists of ordered pairs AB such that A is either equal to or greater than B. Now let us see if it is reflexive. To be reflexive, A comma A must exist, which means that A is equals to A. So here A is either greater than or equals to B. So that means I can say that yes, it is reflexive. Okay, now let's see the second condition, which is anti-symmetric. Now to be anti-symmetric, if A is greater than equals to B, and then B cannot be greater than equals to A. Is it true? If A is greater than equals to B, if A is greater than B, then B cannot be greater than A. But if A is equal to B, then it's quite obvious that B can be equal to A, right? So hence it is anti-symmetric. Okay, now let's see if it is transitive. To be transitive, okay, if A is greater than B and B is greater than C, then it is quite obvious that A is greater than C. And if A is equals to B and B is equals to C, then also it is quite obvious that A is equal to C. Hence it is completely transitive. So this relation is reflexive, antisymmetric and transitive. So I can say that this relation is a relation R is a partial order. Relation R is a partial order and hence Z comma greater than equal to is a poset. Now we will look at another kind of problem. I name it as problem 2. Here I'll be given the relationship matrix, and looking at that matrix I have to find out whether the relation is a partial order or not. Let's see. The first matrix that I'm given here is okay. Now I know that this relation is from the set A. Let us say if this relation is on set A. So I know that this relation R is from set A to itself. That means the rows and columns will be of the elements from set A itself. So the rows also I name ABC and columns also I name as ABC. Now if I look at this matrix, I know that the non-zero entries of the matrix represent the relation. If I give the relation name R, then obviously the matrix for this relation will be represented as MR, and I clearly know that all the non-zero entries represent the relation of the on this particular set. So if I say R is equals to, now clearly you can see here A and A are related, so A comma A. Then you can see A and C are related, so A comma C. Then B and A are related, so B comma A. Then B and B are related, so B comma B. And then C and C are related, so this is my relation set which consists of ordered pairs A comma C, B comma A, B comma B and C comma C. Now let us see if it is reflexive. To be reflexive, all the elements of this set must be in the form of ordered pair A comma A. So I have A comma A here, I have B comma B here, I have C comma C here. So yes, it is reflexive. Now let's see if it is antisymmetric or not. Now to be antisymmetric, if I take BA and BB as AB and BC, right? Because if I take AC and CC, so I know if AC and CC exists, then AC must also exist. So obviously AC exists here, and we know we cannot repeat the elements of the set. Okay. Similarly, if I take these two ordered pairs AA and AC, then again AC must exist, which exists. So again, since I cannot repeat the elements of the set, so that means for every ordered pair AB and BC and AC exists over here. So this is antisymmetric also. Now let's see. I'm really sorry. To be antisymmetric, if AB exists, then BA must not exist unless A equals to B. So here I can see that AA exists and that reverse of AA is obviously AA, but here A is equal to B or A is equal to A. Then if BA exists, then AB must not exist, which is not existing here. If AC exists, then CA must not exist, which is not existing here. So I can say it is antisymmetric. Now let's see if it is transitive or not. Now to be transitive, I will see AC and CC. These are the two ordered pairs having a common element. So AC must exist. Yes, AC is existing. Then again I will take AA and AC. So that way an AC must exist again. Yes, it is existing. So that means it is transitive also. So since this relation is reflexive, antisymmetric and transitive as well, so I can say that relation R is a partial order. Okay. Now we will see another matrix. Again I give this matrix for the relation R the name MR. The elements of the matrix are 1 0 0 0 1 0 1 0 and 1. Okay, so the rows are also ABC here and the columns are also ABC here. Now obviously by seeing the non-zero entries of the matrix I can find out the relation. So the relation is like A comma A, then I have B comma B, then I have C comma A, and then I have C comma C. So I can clearly see that this relation is reflexive because I have all the elements in the form A comma A. A comma A is here, B comma B is here, and C comma C is here. So this relation is reflexive. Okay, now let's see if it is antisymmetric or not. Now to be antisymmetric, I know that if AB is here, then BA will be here only if A is equal to B. So rest for other elements it shouldn't be there. So if CA is there, then AC is not here. Rest all the elements are equal. Hence I can say that it is antisymmetric also. Now let's look at the third condition, transitive. Now to be transitive, if AB, BC are there, then AC must also exist. So there is no such common element. AA and BB cannot be taken as AB, BC. Then AA, CA cannot be taken as a pair AB and BC because there is no common element. So there is no common element here, there is no common element here, there is no common element here. So there is no question of a common element. So that means if AB and BC do not exist, then we do not require any AC to exist also. So by default then it becomes transitive. So that means I can clearly say that it is reflexive, it is antisymmetric, and it is transitive also. So here also I can say that the relation R is a partial order. Okay, now let's look at one last problem of this type. One more matrix. So again, if I give this matrix the name MR, which represents the matrix for relation set R or relation R, and the elements are like this: 1 0 0 1 0 1 0 1 1 1 1 0 and 0 0 1 1. So elements would be A, B, C, D in the rows also and in the column also, since this relation is on the same set. So now I can clearly determine my relations set. It is A comma A, then it is A comma C, then it is B comma B, then it is B comma C, then it is C comma C, and then it is C comma D, then it is D comma A, and it is D comma B, and it is D comma D. So I can clearly see that for all the elements of this set, an ordered pair A comma A is existing in the relation. So A comma A is there, B comma B is there, C comma C is there, and D comma D is there. So yes, it is reflexive. Now let's move on to the other criterias. So is it antisymmetric? Anti-symmetry says that if AB exists, then BA must not exist. So if AC exists, then CA must not exist. So CA is not here. If BC exists, then CB must not exist. CB is not here. If CD exists, then DC must not exist. DC is not here. If DA exists, then AD must not exist. AD is not here. If DB exists, then BD must not exist, and BD is also not here. So yes, it is anti-symmetric. Then is it transitive? So to be transitive, let's take all the common pairs AC and CD. That means if AC and CD are there, so AD must be there. Is AD anywhere here? No, AD is not here. Okay, let's see if there is any other common pairing. Okay, if CC and CD is here, then CD must exist, which is existing by default. Okay, then if let's see DA and AA. If DA and AA exist, then DA must also exist, which is existing by default. Then if DB and BB exists, then DB must also exist, which is also existing by default. Then if BC and CD exists, then BD must exist. So is BD anywhere here? No. BD is not here and AD is not here, which must exist as per the rules of transitive. So that means it is not transitive. This relation is reflexive. This is anti-symmetric, but this relation is not transitive. So I can clearly say that this relation R is not a partial order.